we're going to talk about finding an arc length. Okay, we're going to try to come up with an expression to find the arc length of this curve between t equals 1, where we have 2, 2, and t equals 3, where we have 8, 6. Okay? Well, let's sketch that really quickly if you want to. But I'll kind of move down and we will kind of talk about how we're going to use calculus to find this arc length by zooming in a bunch. And when we zoom in a whole lot around a certain section, what happens to, a curve when you zoom in on one specific section a lot of times? Yeah, it becomes like linearized. So we end up with, this that pops through our screen. Okay? And that's just that. Well, here is kind of the length of that small piece of curve, right? It's whatever my distance is from there to there. How would I calculate that distance? Well, I will pretty much know where this point is and where that point is. And I'll kind of know this length, how much that's going to be. And I know this length, how much that's going to be. So what are we thinking? Mr. Famous dude came up with a theorem. Oh, Mr. Pythagoras came up with his Pythagorean theorem. Well, we have some x length and some y length, and we will say that L is just equal to x squared, or L squared is equal to x squared plus y squared, which means L will equal the square root of x squared plus y squared, right? That's just distance formula, right? Well, x and y could be a little bit better explained, right? Because we are zoomed in a whole lot on this segment, okay? We're talking about zooming in a lot. So what would be this x distance? Really, really what? Small. Very, very small. Almost infinitely small. So small that we could say that it's an instantaneous change in x, right? And it would be the same for our y distance here. It'd be so small that we would say that it's instantaneously small. Very small, infinitely small, not instantaneously small. Be infinitely small, both the dx and the dy, okay? So we're going to say a length of a tiny piece of the arc, which we can kind of say is dl dt, or dl, is equal to the square root of dx squared plus dy squared. We got that? That's super important. Okay. Well, okay, I now have something that can help me find the length of a very, very tiny piece of the curve. But I want the length of the entire curve. What operation can I do to take maybe this length of this tiny piece and get the length of the entire arc? And what would the integral do, Mr. Darnell?
Just add up all of it.
Beautiful. We could take an infinite sum from some value to some value, we'll figure out what those values are, of all of my tiny dx squareds plus my tiny dy squareds. And this is kind of the conceptual idea behind finding the length of an entire arc. Just take a sum of all my tiny dx's and my tiny dy's. Okay? This is where everything comes from. because we will take a parametric equation. Let's say we have parametric equations. Well, right now it's like I can't really calculate this because I don't know with what respect to what variable I have. This is kind of missing here, and I don't know what these numbers are. Okay, so let's see. Parametric equations are defined by what variable? T, right? So I'm going to want dt here. And if I want dt there, that means I'm going to want t's here. Well, I can't just take this thing and just multiply by dt. That would be changing what I have. But what could I do to not change this? What can you multiply something by to not change it? What number? 1. We can multiply by 1, right? So I can't multiply that by dt, but I can multiply it by what? That has a dt in it. Exactly. The expression for 1 using dt. So I'm going to multiply the top and bottom by dt over dt. Right? Cool. Well, I'm going to leave this dt here, but I'm going to do something with this dt. I'm going to move it inside that square root. Let's see what happens when I move it inside this square root. Well, can I just put dt underneath the square root? What would happen if I wanted to take that dt and move it in there? It'd have to be what? Yeah, distributed, but as a what? Just as dt? As dt squared. Okay? So if it pops in, all of a sudden it's dx squared plus dy squared times, now it's in the denominator, so it's going to be 1 over dt squared. And now I got a dt out front, and now since I'm with respect to t, I can go ahead and say, oh, from 1 to 3, these being t's, because I'm going with respect to t. Infinite sum of the change in my times. Okay? Well, guess what I'm going to do, Mr. Keneally? I'm going to distribute that in. And I have from 1 to 3 of the square root of dx squared over dt squared plus dy squared over dt squared dt. Well, that's nice and all, but I can make it look even nicer by going square root of dx over dt squared plus dy over dt squared dt. Now we have an arc length. So I said 1 to 3 just for this example, but a to b of the square root of dx over dt squared plus dy over dt squared times dt. This gives us the length of my curve. Incredible. And it just came from the Pythagorean Theorem, which is also how we calculated speed, right? Right? But speed, we don't want an infinite sum. I just want the length of my velocity vector, which would be dx dt squared plus dy dt squared square rooted. With an infinite sum, all of a sudden, I'm going to take a summation of all of my kind of velocity vectors, if you think about that, because it's just going to linearize. It's going to look like my curve at that specific point. Okay? So here is your arc length formula for a parametric equation. Well, guess what? We're going to use rectangular equations. Let's say this is some, y equals version of x. Again, I'm going to take an infinite sum of my dx squareds plus my dy squareds. But typically, what variable, d what, is on the right when I'm talking about a rectangular equation y equals f of x? It's usually dx, right? Sometimes we did dy if we went up and down, right? But we typically went dx. Again, I can't multiply this by dx, though, because I'd be changing it. I need to multiply it by a version of 1. So what do I multiply it by? dx over dx. Great. That's dt. Fantastic. Well, this dx is going to stay on the outside. I'm going to move this dx into my square root. And what's going to happen? Well, same thing that happened before. I'd have dx squared plus dy squared times 1 over dx squared times dx. Then I would distribute that. And I'd get dx squared over dx squared plus dy squared over dx squared times dx. Can I simplify this? Heck yeah. Dx squared over dx squared is just 1. Dy squared over dx squared is not the second derivative. It's not d squared y over dx squared. It's just the first derivative squared. Now we'll know the numbers a and b. For this situation, we're talking about with respect to x. So the numbers are going to be x's. This would go from 2 to 8, where these are x's. And we could say it's a to b using x's. This is arc length for a rectangular equation. Okay? It's either between two t's of dx dt squared plus dy dt squared, or it's between two x's of 1 plus dy dx squared. Okay? Let's do a couple quick examples. Page 3 on your homework packet. These are the problems 11 and 12. A curve C is defined by the parametric equations given. For each problem, write an integral expression that represents the length of the arc of the curve over the interval. Again, you won't have to create the formula, but it might help if you just think of your infinite sums of your Pythagorean theorem, dx squared, dy squared. And then you think, okay, for parametrics, I want dt. So that's why it's dx over dt squared and dy over dt squared. You know, maybe that helps you. Maybe not. Yeah. No. I mean, you could, but you would just have to go dy, and then it would be dx over dy, which is the reciprocal of your tangent slope. And we were like, we don't like to do that often. So, but you could do it. But dx over dy, all of a sudden, we don't want to do that anymore. Okay? So, here we go. This would just be the integral from 0 to 2 of the square root of dx dt squared, 2t squared, plus dy dt squared, 3t squared, squared, dt. That's it. You got to know how to take the derivatives. For 12, from negative 2 to 2, nothing fancy. Don't change anything up. Square root of dx dt squared, 2e to the 2t squared, plus dy dt squared, 3 squared, dt. And you can plug that in your calculator. Probably the hardest part of these problems is plugging into your calculator, because sometimes you'll have parentheses inside of parentheses inside of parentheses. So just be careful. Now, distance. Let's look at this question. This is number 11 from your packet. Forget which page. The 11 that you didn't do. The 11b that you didn't do. The position of the particle at any time t greater than 0 is given by that. Find the total distance traveled by the particle from 0 to 5. Okay. Well, you know we're using the distance formula here to find this arc length, but if you think about a parametric equation, you know, it's got some sort of arc that it's traveling. Okay, this is an object, and it's traveling in a direction, right? If they ask you what the distance is that this object traveled, they're trying to find this total length here. So if you're asked for the distance, you immediately think, oh, I just need to find the arc length. Number 4 in your AP free response packet talked about the perimeter of an object. Well, guess what you're going to be looking at? Arc length. Okay? So, find the total distance of the particle traveled from 0 to 5. Well, let's just at least write down the integral. 0 to 5, square root of your dx dt squared plus your dy dt squared. 2t squared plus 2t squared squared. Typically, you'll never be asked to do a problem like this without a calculator, or if it is a problem that is asked without a calculator, they will just tell you to write the integral and not to evaluate. Okay? Well, look at your quiz that I just gave you. Look at number 3. Now we have a rectangular graph, y equals x's. Well, you're asked to find the length of the curve y equals x squared over the interval of x equals 0 to x equals 3. They just say 0 to 3. It should be x equals 0 to 3. Okay? Again, how are you going to remember the formula? Well, think about it. We'll take an infinite sum of my tiny dx squareds plus my tiny dy squareds. I want dx here, so I need to then bring in dx squared here. This turns into 1. This is not the second derivative, but the first derivative squared from 0 to 3, or from a to b. Okay. Last one. Simple. 1 to 5 integral 1 plus log x squared dx. Type it in your calculator correctly.
Does it matter if it's in this mode or if it's in the T mode?
No, it does not matter if you're in function or parametric mode on your home screen. So you should just get 4.367 ... Oh, my bad. The derivative, dy dx, which is 4.367. Okay? That's it. So again, the rest of those free response problems, I'd kind of, practice for the test by doing one from scratch, like as a practice test question. If you see a distance question, arc length. Okay? The quizzes will be online. It's only these 3 lessons, all on parametric. I think it's a good test. I think we should be able to do well in it. But probably the ones that we'll struggle on are the free response questions. Okay? Sweet. One of the shortest lessons of the year.